All right, so this is a review for exam 3. We'll be discussing about second law thermodynamics and we'll focus on the performance of engine like heat engine, or it could be a refrigerator, or it could be heat pump. So that's what we'll be doing. So we will, as I said, we will be focusing on the performance of actual and ideal performance of the heat engine and refrigeration and heat pump. That's what we'll be focusing on. The second law of thermodynamics um, can be defined based on Kelvin-Planck statement, which is related with the heat engine, and we want to find the performance of the heat engine. And for finding the performance of heat engine, it is given by the thermal efficiency, and thermal efficiency is um, in the heat engine, the work is produced, so how much work produced divided by how much energy you supplied. So QH is the energy supplied, and this is the amount of work. So the basically thermal efficiency is how much work you do based on how much heat you supplied. So that's conversion. So you are trying to convert heat to work. Okay, and the Kelvin Planck statement says that so if you substitute this W net by QH minus QL here, this is what you get. It says that, the Kelvin Planck statement says that this QL can never be equals to 0, or in other words, there will be always some heat that is rejected. So which means you can thermal efficiency never get thermal efficiency equals to 1 or 100%, so it's impossible. So that's what the Kelvin Planck statement is. You can never get um, thermal efficiency of 100%. Otherwise um, it would not obey the Kelvin Planck statement. So that's about the Kelvin Planck statement and how you find the thermal efficiency. And the Clausius statement relates to the refrigerator and heat pump. And in this case, instead of thermal efficiency, we find what is called as a coefficient of performance. For refrigerator, if you think about this, how refrigerator work, you have to look for the COP is always whatever the desired output divided by the W net, because in the refrigerator you need to do the work in the compressor, right? So the desired effect is, if you think about food, how much food and the heat you take away from food, that is QL, and then W net in, right? So this is what it is, and if you simplify, this is what you get. Higher the value of COP, better the performance of um, the refrigerator is. And the Clausius statement says that you cannot um, take heat from colder temperature to higher temperature unless you apply the some amount of work. So without supplying some amount of work, you can't do that. So that's what the refrigeration cycle and heat pump. The difference between heat pump is the desired output. In heat pump, or maybe like you want to heat some space at home, so QH is our desired output in case of heat pump. Okay, and then divide by the required input which you supply here in the compressor. So this is the formula for COP for the heat pump. These all are for the actual cycle. You can always compare this with what we call as ideal cycle, reversible cycle, or Carnot cycle. And we did this in the class as well. When it is a ideal cycle or reversible cycle, QH by QL, or the reciprocal of that is the same thing. So QSTH here, and by TL, when it is reversible or ideal, this formula is handy, and this is what is satisfied. So you can replace this QHQL here in COP as well as in the thermal efficiency if it is a Carnot or ideal cycle. So if you replace that for Carnot heat engine, so QL by QH would be TL by TH. So this is handy for finding the thermal efficiency for reversible heat engine. And when that is the case, this should be equal, if you see here, so thermal efficiency would be equals to thermal efficiency if it is a reversible heat engine. So this equals to 1 minus QL by QS. So these formulas are very important. And sometimes even it may not tell you like it's a reversible or ideal. The other way of saying is if it's the turbine, it says maybe maximum power production. So maximum power production is possible when it is a Carnot or ideal or reversible. You need to understand that. In compressor, it becomes reversible when we have to supply the minimum amount of work. So you need to look for the wording, and not necessarily always you will be told it's a Carnot or ideal or reversible. So you need to look for the wording. Okay. And for a Carnot refrigerator, again reversible refrigerator, we are just replacing QH by QL by TH by TL, and so this formula can be used when it is a reversible or ideal or Carnot refrigerator. And similarly, if you replace um, the QH by QL by the temperature, this is the formula you can use for the heat pump. Remember, these COP and thermal efficiency formula in terms of temperature can only be used when it is a reversible. This is a special case. And the most important thing when you do the calculation, whenever you are using the temperature, it involves the ratio of temperature, so it has to be always absolute temperature scale. For instance, if you are doing in SI unit, it has to be in Kelvin. If you are using in US customary unit, it has to be Rankine. So don't use the temperature in Celsius. Don't use it. Don't use in Fahrenheit. Okay, so you should not use the temperature other than the absolute temperature scale. This is very crucial. Otherwise, you get everything wrong. So this is kind of overall picture, understanding how you can find the actual and ideal performance of different cycles. Okay, some of the formula, these are exactly what we did in the class. For instance, here this is a actual cycle, and you have been asked to find the thermal efficiency. So in this case, you cannot use the temperature that are based on um, you cannot use the formula that are based on temperature, because these are only used for Carnot heat engine or ideal heat engine. But here it doesn't say anything like it's a Carnot or so you cannot make use of this formula. Okay, so it's very crucial to understand when to use which formula. But if it is a Carnot heat engine like here, then you can use the formula that relates to the temperature as well. So in this case, again, when it is a Carnot, then Carnot, then it becomes 1 minus TL by TH. This is also equals to 1 minus QL by QH. So when it is a Carnot, you can always use this one. And also other important formula being QH by QL is TH by TL. So when it is a reversible or it's a Carnot or ideal heat engine. Okay, so keep that in mind. So you can use this one, and you can also use this one to find the unknown. So this is for the Carnot heat engine. Similarly, you can do it for the heat pump as well. And in this case, I think it doesn't say anything about whether it's a Carnot heat pump. So if that is the case, you cannot use the formula that relates with the temperature. Okay, so you can use this formula to find out how much is this COP. All these problems are the problem that we did in the class. Okay, so just I'm going through it just to make you understand like which formula to be used for a particular purpose. Okay, but if it is a Carnot like here it says a Carnot heat pump, then the formula based on the temperature can also be used. And remember, the temperature has to be always in absolute temperature scale. Like here we convert it to Kelvin, and also you need to be careful about the unit as well. When it is a ratio, always have the unit of temperature in absolute temperature scale. Okay, so that's kind of